I guess now we're gonna take a look at the stuff we actually had before, and I'm not sure if I'm in the right place. I think I misentered the page number. Let's see. Where is that? Chapter 9. So we actually in 10.5. So it's like 870 or something like that. Yeah, like this way is better. Okay. So looks like we stopped at section 5 of that chapter 11, and it looks like for what happens. I think I'm in the wrong chapter. I'm not sure what is going on. I'm not entering correct page or something. Anyways, let me just scroll because I'm one chapter behind. Okay, so now we're here. So it looks like in those polar coordinates, we have been graphing back in trig class, and then I tried to show you major techniques to produce those graphs. And we also saw the formula for the area, looked at one exercise in polar coordinates. The key part is to realize that if you are finding the area under the curve in the rectangular coordinates, so you're gonna integrate some function f from a to b dx, then of course function f of x. The function in the polar coordinates is some kind of function of variable theta, and therefore, since it's angle, then you're going to have the region from alpha to beta integrated to get the area of sector, which is bounded by that angle of your function of angle theta d theta. Notice that R does not really participate in all of these cases because R is like y function of x. So x is our independent variable. So same with the polar cases, theta is independent variables. So it's good to realize that even though they put here integral of r squared, but it's actually r of theta. That's how one should read it, because again, that's function with respect to theta, and then the angle theta varies from alpha to beta. So that's why they being specific in terms of those limits of integration. And it's all actually going to boil down to get the angle, and that's what I was actually trying to do last time. If you remember, the angles that we produce are always going to be tangent to the graph, and that's advantage of graphing, I guess. And then we'll see from angle, like in this case was negative pi over 6 to positive pi over 6 is what we actually try to find the region. And again, it was bounded by that curve function r of theta. So they consider in various other examples here, like in example 2, even though the integration part seemed to be kind of straightforward, but all of the work done before to produce the actual limacon, right? That's how they call it. The limacon, the region that has a hole here on the inside, is what we have to find. And why is it having a hole? Well, because it looks like for the angles in between pi over 6 to 5 pi over 6, our R is going to be negative. I think I should graph this figure, because once you have a graph with you, then everything is pretty straightforward. But the part they really skip here is how they produced that graph, right? And that's what I'm gonna try to find out. So the R, when is it gonna be the smallest? Minimum. Well, looks like it's gonna be when we have the value of sine equal to 1, right? So sine theta is 1, and that's going to be 1 minus 2, so it's -1. And then you can see the values for the function when sine is equal to 1. I'll make a picture here. Sine is my y coordinate, so it's for angle pi over 2 plus period 2 pi k, so it looks like I just care about angle pi over 2, because we don't have 2 theta or 3 theta, we just have a single theta. So just one participates in our circle. Maximum when we have plus, in other words, when we have minus and a minus, right? That's how we get 1 plus 2, which is 3. And what happens when we have a sine theta equal to -1? Well, this is this point on the bottom. It's negative pi over 2. You can put negative pi over 2, or if you want to go with the angles in between 0 and 2 pi, which most people deal with, then you're going to get 3 of those pi's over 2, right? And finally, 0, that happens when we have 1 minus 2 times 1/2, right? So sine has to be equal to 1/2. And when sine is equal to 1/2, well, 1/2 on the y-axis is for these two angles, and theta then will be pi over 6, right? And then you take that pi over 6 of pi, so it'll be 5 of these pi's over 6. So pi over 6 and 5 pi over 6. So that's when we get to the 0. And now I guess our picture starts to make a little bit more sense, right? So let's try to produce it now. So it looks like when you start at where? Well, it looks like I can actually start graphing with maximum at value of 3 that corresponds to angle 3 pi over 2. So this point will be here. So that's the maximum point. Now I need to return to angle pi over 6. And at pi over 6, we're going to go to so-called poles. So the distance to the pole will be smaller and smaller and smaller, and eventually we'll get to here. So what happens after that? Well, after that, from pi over 6, we're going to go to our minimum case, which is -1, and that appears when theta is pi over 2. So to depict that, even though I take angle pi over 2, But since radius is -1, I'm reflecting to the other side. So the inside part is going to be, instead of going like that, will be all reflected and go like that. And then it will return back at the angle 5⁶, analogous. Please notice that this graph seems to be symmetric through the y-axis, right? 5⁶ is here. It's interesting to try to notice that, but anyways, so that'd be a circle, and then the other side is going to be just repeating the same thing, and that's how the graph is being produced. So then what people notice, if they want to find the area bounded, let's see what they want, between, that's the word, they want an area in between, then what they want to do is take the origin of that a heart-like picture, and that heart picture goes from angle π/6. Actually not, it will go from angle, even though here's 5π/6, but if you try to integrate from π/6 to 5π/6, you will get the area of this little pink thing. Okay. So if you integrate from π/6 to 5π/6, because it's all reflected up there, kind of down. See? So you really need to trace these curves very carefully, and that's the message in here. So if you get this carefully set up, then everything will be fine, because all you do is you just integrate your function, which is r², so it'll be 1 minus this 2 sine theta squared. It looks like you're going to just have to square this, and you're going to end up with 3 integrals to take, and there'll be number 1, then 4 sine theta, which is nice and straightforward, and then sine squared that you break as a cosine of doubling. So that's the little one. That's the whole that you will be actually subtracting. And then the big area, where is the big area? Let's see if it's clicked somewhere. So we gotta, they put a big area. So notice that for the big area, they say integrate from of the origin line inside. So what is going on? So for the little one, I got that. So I guess I need to somehow get to the from 5⁶ all the way around to π/6 plus pi. So that's how you're going to get the big area, which is 13π/6. So you don't really utilize sometimes angles in between 0 and 2 pi. And again, it's all coming from construction, because otherwise, if you don't construct it, how would you know what they're really talking about here? So I guess in this section, my goal is to just give you a little bit of introduction into the process. So this way you could produce out of your graphs various areas. So another interesting story, if second curve comes into a play, so what happens in that case? Remember, with 2 curves, we used to deal, let me clean it, with upper curve minus lower curve, right? That's how we used to integrate, and again, XY coordinates, but what about polar coordinates when we are dealing with angles? So it looks like I need to, so here's one curve, let's say here's another curve. So points of intersection we call as A and B, for example. and then say upper curve is function f, lower is function g. So we go f minus g, right? From a to b, and that's in what xy coordinates when you go dx. Now for the case here on the figure down below, they have a first curve and a second curve that I need to first of all intersect. So I need to know from what angle to what angle they will give us points of their intersection. So they simply produce the system of equations, and then they set it up, and then they find those angles. And as you can see from the picture, one of them is positive pi over 2, and the other is 3 pi over 2. So those 2 points, that's what they hear about right now for their particular region. And from there, they have a start. I'm not sure if they integrate it actually, because it'd be, I think, a little bit tricky. They just found points of intersection, and that's it. Because you can see if they actually started to ask you to find those regions, it might take a while, right? And that's actually what happens in example 3 when they look at the area in between curves. So the key idea again was to find the actual angles or points. We don't say points now, it's the angles at which we have the intersection of those two curves. And then we could actually get the area of that region. They looks like highlighted it in pink. And technically from the picture, they noticed that you don't have to go all the way to 4 pi over 3. They could just stop at pi and double that region. So again, geometrically, there are all kinds of little shortcuts that we can produce. I'm not sure if that's really that necessarily, but just to see how it goes. So anyways, we now produce actually not that exactly what I produced for the picture, because if you're just integrating the one curve here, that's like an upper, and the lower will be there, right? So you need to subtract from the upper the lower curve, and that's how you will get that picture. Because if you just integrate in upper, you will get up to that dashed line. But if you subtract the lower, then you will get the whole thing. So it's not that straightforward. The point is probably integration is not such a big of a deal, but more is to set up the picture, set up the actual integral. And then there is also a formulas that come with the arc length. And well, that's kind of analogous to what we already saw before. So maybe I'm not gonna get that deeply into this because they actually don't prove this formula. Remember, we had the one for polar coordinates that was dealing with the square root from square of function for x, and then square function for y. And they're all in terms of theta, so it's like d theta. So now they actually turning this into the arc length function. So that was arc length, we used to call it as s, right? So from say alpha to beta. And now we have those coordinates r cosine and r sine y for some function r of theta. So now you have these two to actually integrate and put them in. And when you start to integrate them, notice that this is product because r also depends on theta. So each of them, you need to take the actual derivative of product and then set up And what you're going to end up with this kind of unusual looking formula. And actually say they have it in exercise 89. It's probably at the very, very end of the section. But they actually expect you to do this. So use the derivative of product. Well, you're going to need a big piece of paper and write it all down. And if you get interested, I think that could be interesting exercise for a project if somebody wants to get extra points. In fact, lots of extra points. I'm sure if you can do it, you're definitely going to ace this class, because that's very interesting to actually go through the process of derivatives of product and set it up in the square root, and it will come out by itself. So anyways, I guess that's pretty much all I wanted to say about this section. I'm not going to ask you to do exercises on that. I just wanted to introduce you with it, because it ends up being all pretty much of the same kind. It's all dealing with a derivative of trig functions, and they all being broken with this double angles or sometimes half angles, and so going basically to the same pattern. I'd rather start to discuss what we're going to have on the final, because it's already been a little while since we were touching some of this stuff, and I'd like to find what I sent to you as a practice final exercise. Let me see what I sent to you. It was here. Okay. So first exercise on the final will be of the type of sign alternating series, which is actually involved power series case. So with power series, we used to have some fun, and we had so many little properties, but particularly for power series, we use this root test and the ratio test. And then we had to test what happens with the end points. So just to refresh, I sent you the exercise that deals with these last digits of your student ID. So I made up, so let's say if last digit is 6, you use 6. If last digit is 7, you use 7. If someone wants me to use any digit, just tell me which one you like me to use. I will use it, or else I'll just use 6. So pretty much same, but the answer is not the same. That's the point. So sounds that you want to use 7. Let's use 7. Good choice. So then series is gonna look like from 0 to infinity. So -1 to the power of n, x minus 7 is raised to the power of n plus 1 and divided by n plus 1. So our goal is to, looks like, utilize the ratio test, because we don't have any power on the bottom. So the ratio test is talking about the limit of an plus first divided by the n's terms in absolute value that need to be less than 1. So then series will converge absolutely. And that's a powerful convergence without this -1, without any sign alternation. And if it's greater than 1, that series will diverge. And if it's equal to 1, then I need to test it. And that's why I need to set up this expression. And for that matter, I'm going to see what is n plus first term comes out to be. And I simply just replace n with n plus 1. So I just put n plus 1 and plus another 1. I say I put n plus 2, but I'd rather keep n plus 1 because it will cancel, right? So then my quotient of this n plus first and the nth term is going to look like, without a -1, of course. Notice that I actually have the absolute value of that term because -1 is not used, but since x is present, I should also put absolute values then. So anyways, everything will be inside the absolute values, and on the top of my fraction, I will have x minus 7 to the power of n plus 1, and another x minus 7 right next to it, which is also going to be divided by n plus 2. And that nth term I'm going to reciprocate. So I'm going to take this, so I don't have to write it with complex fraction. So I'm going to just reciprocate, and that's n plus 2 actually, because plus 1 and plus 1. So I'll put n plus 1 on the top, and x to the power of x minus 7 to the power of this n plus 1 on the bottom. So I do this to be able to get my favorite canceling step, just like that. So we end up with a limit. So now I can put it all in the limit. I could put it earlier, but so n goes to infinity, of course. So we have n x minus 7 inside the absolute values. And it's also multiplied by n plus 1 over n plus 2, which is approaching to number 1, right? This goes to 1. You use L'Hopital's rule, or you could just take a quotient of leading coefficients 1 over 1. So this needs to be less than 1. Since x has nothing to do with n, I ended up with the inequality that says x minus 7 is less than 1. So for all values of x here, we have this absolute convergence, and that's exactly what we're testing on here. So we get a convergence for the series, and looks like x minus 7 is going to be in between of negative and positive 1. And therefore, when I add 7 to both sides of this inequality, I'm going to get 8 here and 6. So here we have absolute convergence right away. Now the question is, what about the endpoints? See, this exercise is a little bit longer, so I need to see what happens when x is 6, and also what happens when x is equal to 8. And I'm working with this series, so I just need to replace in it those two numbers. So here, now I will keep minus sign. So what happens when x is 6? Well, we have a -1 power of n times 6 minus 7 to the power of n plus 1 over n plus 1. You probably recognize the harmonic series, right? Just to write it here. 1 over n, or 1 over n plus 1, is called harmonic series. So this is called divergent series if all terms are positives. So what happens in our case? It looks like it's -1 to the power of n plus 1 times -1 to the power of n. So this series is going to look like -1 to the power of 2n plus 1, which is always going to be odd, isn't it? So what I can say is just a -1 over n plus 1. Why is that? Well, this is odd number. You take when n is integer, right? Because n actually varies from 1 to infinity. or from 0 to infinity. So it's going to be power of, when n is 0, is going to be power of 1. When n is 1, power of 3. When n is 2, power of 5. So you raise -1 to negative powers, you're always going to get negative. So you just put minus here in front. And this is divergent harmonic series. The name for this was harmonic. Doesn't matter if it's n or n plus 1. It's still the same thing. You can substitute instead of n plus 1, put k. And you can get 1 over k if you really want. But it's good enough to realize that this is divergent and harmonic. So now what happens with the case when x is equal to 8? Would be the power of -1 in that situation. Well, looks like if I subtract 8 and 7, I'm going to get a positive one. In other words, it's not going to affect anyhow this piece. So let me maybe use another color. So if I have a series, again, it's still -1 to the power of n, and now we put 8 minus 7. So this is the key part for us right now, power of n plus 1, and it's still divided by the same thing, by n plus 1. So notice this is going to be number 1, right, raised to some integer power. So it's just number 1. So I don't even need to bother to write it. So I get a sine alternating series. So what's happening with sine alternating series? Well, it's going to be convergent as nth term goes to 0, right? Nth term is what? 1 over n plus 1. We also had extra little fact that has to be a monotone series, so it's not moving away, but well, 1 over n is monotone, it's just gradually goes to 0. So it is convergent. Therefore, my interval is going to be including 8, and that's going to be the interval of convergence. And that's the kind of exercise, I think, that very well reflects what we learned about series, right? And that's pretty much all I want to